Welcome back to this next video in which we are discussing the definition of a ring. Okay, so we are currently in the process of constructing a ring, and what we've seen so far is that you start off by creating a set of symbols here, and then what you're going to do is define an addition composition law on this set of symbols. Okay, and we want this addition composition law to obey the axioms of an abelian group, and we've just beamed through what those axioms of an abelian group actually are. Okay, now, at the moment then, the structure which we have, this set of symbols with an abelian group addition composition law on, is just an abelian group. We want to now take it beyond that, we want to turn it into a ring, and to do that we need a second composition law. Okay, and again this is going to be a composition law where you can compose any element of the ring with any other element of the ring. So once again, we'll be able to represent it with a composition table here. Okay, and this is going to be the multiplication composition law, which I'll colour in here in red. Okay, so just writing out its title here, this is going to be multiplication. Okay, so what we're going to do once again is we're going to, in this great big table, give every element of the ring a row that will be dedicated to it. So we'll put all of the elements of the ring down here. Okay, and I'll just draw a few rows here, so this table will be split into rows, and what we will do is dedicate a row to every element of the ring. So every element of the ring will get a row dedicated to it. Okay, similarly, every element of the ring will get a column dedicated to it. So up here in the title space for the columns, we will put every single element of the ring. So here are a few columns drawn on here. Okay, and then what we'll have to go through and do is to fill in the answers in all of these these little squares here, these little boxes in our actual table, and that will define what any element of the ring multiplied with any other element of the ring is. So, if we want to know what x multiplied by y is, and I should state that usually it's conventional not to actually stick in the multiplication symbol. Often when we mean multiplication, we just write the two elements next to one another like so. Occasionally you can stick in the actual multiplication symbol there, but it's more conventional just to write them next to each other. Okay, so the way that you will actually find out what is x multiplied by y then is you'll go to your great big multiplication table here, and you'll take the row dedicated to little x, you'll take the column dedicated to little y, and then the box, which is the intersection between the row dedicated to little x and the column dedicated to little y, that's going to contain the answer to what x multiplied by y is going to be equal to. Okay, so you need to go through then and fill in all the entries in this multiplication composition table and define what any element of the ring multiplied with any other element of the ring actually is going to be equal to then. Okay, now, once again, you are not allowed to just fill this in arbitrarily. You can, of course, do that, but you will end up with something that is probably not going to warrant study. It's not going to be very interesting. Okay, so in order for our number system that we're building here to be very, very interesting, in order for it to fulfill the axioms of a ring, okay, and all rings are very, very interesting algebraic objects, this multiplication table needs to now obey a bunch of axioms, and a lot of them are analogous to the axioms that we insisted on addition obeying. Okay, so where am I going to put these axioms? I think we'll have to go over the page to put them, unfortunately. Okay, so I'll just straighten this up. Right, so let's do then the 4 axioms that we want multiplication in our ring to actually obey. So axiom number 1 is exactly like axiom number 1 that we wanted addition to obey. It's closure once again. Okay, so if I take any two elements of the ring, so for all little x and little y that you can possibly dream up from the ring, I want x multiplied by y to also be an element of the ring. And again, that quite simply says that I want all of the answers in the multiplication composition table to actually be from the ring. Okay, so going back to my picture here, all of these answers in the multiplication table here, you're not allowed to suddenly put new symbols in as the answers, okay, just as you weren't with the addition table here. Okay, all of the answers have to be back within this original set that we started off with, this set of symbols that is the ring. You're not allowed to suddenly make up a new symbol and stick it in as the answer to two elements of the ring multiplied together. That's not allowed. Okay, so we're insisting on closure then. Okay, and that's axiom number 1. Okay, axiom number 2 is associativity, multiplicative associativity. So again, what we can consider is we can consider the multiplication of 3 elements of the ring together, and we have the same problem here as we had in addition. Okay, our multiplication table tells us how to multiply any 2 elements of the ring together. It does not tell us how to multiply 3 elements together. So to give multiplication of 3 elements together a meaning, you have to break it down with brackets into the multiplication of just 2 things at once. And then the problem arises, well, there are 2 ways of doing that. Okay, either you can put the brackets around the x multiplied by the y, okay, and then this means firstly multiply x and y together to get some new element of the ring, and we know that will be an element of the ring thanks to axiom number 1 here. And then take that new element of the ring and then multiply that with z again in the multiplication table. Okay, and what we're going to insist is that that way of doing this multiplication of 3 things has to give the same answer as if we do it the other way, okay, which is we put the brackets around y times z. So for this side, the right hand side here, this means firstly multiply y and z together in the ring multiplication table, get some answer that's again back within the ring, and then take x and multiply it with that answer in the ring. And of course that is a different way of doing it. That will give a different entry in the multiplication table, but I'm now going to insist that these 2 different entries in the multiplication table are going to have to be equal to the same thing, and that has to be true for all x, y, and z are in the ring. And again, that's a very non-trivial property. If you were to try and actually create a ring multiplication composition table, you would struggle to get it to obey this unless you knew what you were doing. You'd have big difficulty getting it to obey associativity. It's very, very difficult to do. Okay, so associativity then is our second axiom that we want multiplication to obey. And our third axiom is that we're going to want a multiplicative identity. So I'll give this one its full title. Okay, so we saw that we have an additive identity in our ring. Now what we're going to have is a similar concept for the multiplication composition law, okay, which is going to be called the multiplicative identity. Okay, so I'll colour this in purple here. Okay, so what are we going to want to be true then? What we're going to want to be true is that there is going to exist an element of the ring which, again, for historical reasons, is always called 1. Okay, so there's going to exist a symbol called 1, which is an element of the ring. Okay, now I will stress this, and I'll stress this again later on. 0 and 1 are always distinct elements of the ring, except in one stupid case, and we'll have a look at that stupid case later on. It's called the 0 ring, and it's the only case where 0 and the 1 can be the same element. Okay, so where the additive identity and the multiplicative identity can be the same symbol in the ring. In all other rings, the additive identity and the multiplicative identity have to be distinct symbols, and we'll see that later on, so I can quite happily put 0 and 1 as separate symbols in the ring. There is one case where that can't be done, okay, but we'll discuss that special case, or stupid case rather, later on. Okay, right, so there exists this element, 1, which is an element of the ring, and this has the special property that 1, and I'll just put such that 1 times x, so 1 times x is equal to x, and x times 1, and I might actually just put the multiplication symbol in there, is equal to x, and that holds true for all x is an element of the ring, capital R. So just like we did for the additive identity, I will now draw a picture for what this actually means in terms of our multiplication composition table, after I've just straightened up my piece of paper here. Right, okay, so let me draw out my multiplication composition table here then. Okay, so here is multiplication. Now, 2 elements of the ring that we are actually familiar with now are the additive identity 0 and the multiplicative identity 1. So I'll just draw these 2 elements on. Okay, so the additive identity 0 will have a row dedicated to it in the multiplication composition table, as will the multiplicative identity 1. Okay, and they'll also have columns dedicated to them, like so. And allow me just to colour this in, and I'll colour it in red, which is the colour we've been using to denote the multiplication composition table throughout. Okay, now we will come back to the rows and columns dedicated to the additive identity. We haven't actually yet looked at the property which allows us to say what those will be equal to. However, we now can say what the row and column dedicated to the multiplicative identity 1 are going to look like. Okay, so firstly let's take this top property here, and it's exactly like the additive identity in the addition composition law, but now we're doing the multiplication composition law. Okay, so 1 multiplied with any element of the ring, so you take any element of the ring, take the column that's dedicated to that element of the ring, here we go, and 1 multiplied by that will be the answer in this box here, which is the intersection between the row corresponding to 1 and the column corresponding to x. Okay, so this box here will contain the answer to 1 multiplied by x, and I've now said that that must be equal to x. So again, that tells us something about this row that is dedicated to 1 here. It tells us that it has a very boring form. Okay, it is just going to look exactly like this up here. Okay, so up here you have every element of the ring up here in this title portion for the columns, and they'll all be in a certain order, and basically all you have to do is copy that entire array of elements of the ring out and put it in this orange row here, and that's what the row corresponding to the multiplicative identity in our ring is going to actually look like in our multiplication composition table. Okay, now let's have a look at what the column corresponding to the multiplicative identity is going to look like in our multiplication composition table. So now let's use this second line here. So any element of the ring multiplied by 1 is going to give that element of the ring back again. So what you'll do is you'll take the row dedicated to an arbitrary element of the ring, little x here, and then you'll say, okay, if we want to multiply this by 1, we need the intersection of this row with the column corresponding to 1. Okay, so that's that box there. So that's going to contain little x. Okay, and again, this is going to be true no matter what element of the ring you choose. So what that means is that this column corresponding to 1 here is going to be very boring as well. It's just again going to contain all elements of the ring, and all the elements of the ring will be in the exact same order as they appear over here in this portion that has the title for all the rows. So all you have to do is copy out this column of elements of the ring here and stick it in here, and that's what the column corresponding to the multiplicative identity in the multiplication composition table is going to look like. Okay, so that's the multiplicative identity, axiom number 3 that a ring must obey, or that the ring multiplication composition table must obey. Okay, now let's have a look at axiom number 4. Okay, so axiom number 4 is the fourth and final axiom that we're going to insist our multiplication composition table obeys in a general ring. Okay, and it has the name distributivity. Now this is where we suddenly link the two composition laws together, because at the moment there has been absolutely no link between the multiplication composition table and the addition composition table. Okay, so it's not very interesting if you just define a set of symbols and then have two composition laws on it, but the two composition laws don't interact in any interesting way, because then you might as well just study them separately. Okay, if there's not some interesting interaction between the two composition laws, then what's the point of having them together, basically? You might as well just study them separately. Okay, so now axiom number 4 is going to change that. We're suddenly going to get a link between multiplication and addition. Multiplication and addition are suddenly going to start playing nicely with one another. Okay, now there are two separate parts to distributivity. There is left distributivity and there is also right distributivity. So I'll start off with left distributivity and then I'll state right distributivity. So firstly, I'll put the first line, so for all the elements of the ring that you can take, so for all x, y, and z that you can dream up from the ring capital R, left distributivity says that if you consider what is x multiplied by y plus z, then that needs to be the same as if you firstly multiply y and x together, and then you multiply x with z, and then you add them together afterwards. Okay, so this is really saying that it doesn't matter if you firstly add and then multiply, or if you firstly multiply and then add. Okay, now let me stress how non-trivial this is. Okay, so let's draw out a little picture for our addition multiplication table, or addition composition table rather, and our multiplication composition table. So I'll colour these in. So let's have the addition composition table here in green. Okay, and let's have our multiplication composition table here in red. Okay, so let's firstly consider what the left-hand side of this equation is actually going to equal. So you're firstly going to add y and z together. So here is y, let's say, and here is z. So we've got the row dedicated to y, the column dedicated to z, and we're going to add these two together in our addition composition table to get y plus z. Okay, this answer here. Then what we're going to do is we're going to take whatever this is, and this will be some element of the ring, okay, and we're going to then multiply it by the element x in the ring. So we're now going to go over to our multiplication composition table. We're going to take the row corresponding to little x here, and we'll take the column corresponding to this element y plus z, and we'll multiply them together, and that's then our final answer, x times y plus z. Okay, so here in yellow then, that's the final answer on the left-hand side. Now on the right-hand side, we're doing something very different. We're firstly multiplying x with y and x with z. So I'll say this is the column dedicated to y, and let's say this is the column dedicated to z over here. So I'll just extend my multiplication table up a little bit. Okay, I'm multiplying these two together, so I'll get x times y here, I'll get x times z here. Okay, so the row corresponding to x, column corresponding to y and z, and then taking these two answers, x times y and x times z, and let's arbitrarily say that this element x times y, its row is down here, and let's say the element x times z, its column is here, and I'm then adding these two together, so I have x times y plus x times z here in my addition composition table, and hopefully you can appreciate that this is a different entry to this one over here. Okay, so the answer to the right hand side here is some entry over in the addition composition law, and the answer on the left hand side is an entry in the multiplication composition law. If you had just made up these composition tables, it would not obey this, absolutely no chance at all. Okay, so if we're going to insist that this is true, it means that the addition law and the multiplication law must be incredible. Their structure is incredible. They must be incredibly well designed. Okay, so that then is left distributivity, and I hope from this argument all I've convinced you is that doing this is very different to doing this. Okay, and to say that the two answers are the same means that there is an incredible structure on the addition and multiplication laws that mean that they are interplaying in this incredible way. Okay, and that's true no matter what x, y, and z you're going to pick from the ring, or at least it has to be true for whatever x, y, and z you pick in the ring if this is going to be a ring. Okay, now we're also going to insist that it obeys a right distributive law, right distributivity, and this is the one that always gets forgotten. Everyone, if they're going to state distributivity, usually states left distributivity. Now, the reason it often gets forgotten is that really, when people talk about a ring, they usually mean a commutative ring. Now, the definition of a ring doesn't actually require it to be commutative. Okay, strictly speaking, if you want it to be commutative, you should say a commutative ring. However, most people work with commutative rings all the time, and if you're working with a commutative ring where multiplication obeys commutativity like addition, left distributivity implies right distributivity trivially. However, in the formal definition of a ring, you don't insist that multiplication obeys commutativity. Okay, we'll add that one on later on. Okay, so you do need to separately state right distributivity here. So right distributivity says that if you have y plus z, and then you multiply that by x, that should equal the same thing as y times x plus z times x. So again, you can either add y and z together firstly in our addition composition law, get some answer in the ring, and then multiply that with x in our multiplication composition law, Or you can firstly multiply y with x and z with x, get two answers within the ring, and then add those together in the addition composition law. And those two ways of doing it must give the same answer. That's what it means for the addition and multiplication laws to obey right distributivity. Okay, so those are the two distributive laws that we're going to insist are true. Okay, and they are laws concerning not just the multiplication table, but obviously also the addition table. They speak of this deep connection between the two, a deep pattern between the two. Okay, and that then is all of the axioms that we're actually going to insist a ring must obey. Now note there are two axioms that you might think are missing from this multiplication list that we want multiplication to obey. Okay, firstly, I have not insisted on commutativity. I have not insisted that x times y is equal to y times x. We'll come back to that later. You don't insist on that for an abstract ring. Okay, in addition, I have not insisted that all elements of the ring have a multiplicative identity, and again, a multiplicative inverse. And again, that's not an axiom of a ring. We do not need the elements of the ring to have multiplicative inverses. Okay, so these are all the axioms that we want a ring to obey. We want it to have an addition law, which is an abelian group composition law, and we want the multiplication composition law to obey closure, associativity, identity, and also the two distributivities, left distributivity and right distributivity. Okay, so I think we'll have a break there, and in the next video what we'll firstly ask is what do the rows and columns, the row and column dedicated to the additive identity element in the multiplicative composition table actually look like, and we can instantly make a conclusion about that from left and right distributivity. In addition, what we'll look at is a way in which we can extend left and right distributivity.